In the last video, we had defined displacement and realized that was the vector that told us how to go in a straight line from an initial position to a final position without regard for the actual path that the object took. We can use this definition of displacement, though, to give us our first pass at defining velocity with what we call the average velocity. So the average velocity will be defined to be the displacement over the time that the displacement took. So again, more symbols to unpack here. If you see a bar over a symbol, that just simply means the average value of the thing. Other notations that sometimes people use is they could write an AVG as a subscript, or they could put angle brackets around the symbol. Those are all pretty common. So again, this delta x bit here is our displacement. And we remember that the delta should be read as change in what? X's position. So displacement is change in position. Here we have, again, this is change in here. And change in what? Change in time. So another way that we could write the average velocity that something is going as is we could expand it out, and say that v bar is my final position minus my initial position over my final time minus my initial time. And I would say 99 and 44/100ths% of the time that you attack these problems, usually T0 will be equal to 0. So usually you can just go ahead and set 0 to be the beginning of the problem. There are times where you can't, though, so this is technically the most correct. And so these should be kind of viewed pairwise. This is the time at which the object was at the initial position. This is the time at which the object was at the final position. So for our dimensions on this, it's going to have dimensions of length over time. And for typical units, good example would be meters per second if we're going with SI units. Again, we could be having, say, something like miles per hour, furlongs per fortnight, whatever. Some unit of length over some unit of time. So we can relate these to our motion diagram here. So let's look at, say, we're going along here. So here is my x coordinate, and what the heck, let's make this feet just to mix things up a bit. This would be 0 here. So at t equals 0 seconds, let's say we've got ourselves a bike here. It's located right here at the origin. Then let's see, we can go over here to 20 feet. This is where it's located at 1 second, 2 seconds, and 3 seconds. And we can see that we're going in what's called uniform motion. We'll rigorously define that later. But for now, it just means constant velocity. So the speed is the same, and we keep going in the same direction. Let's go and, just to mix things up a bit here, let's look at this time interval right here. Actually, better yet, let's do this interval right here between t equals 1 and t equals 3 seconds. So we can go ahead and figure out what our average velocity is over that interval. You would say the average velocity is the change in the position over the change in time. So this would be our final position minus the initial position over the final time minus the initial time. So this would be located at 60 feet. Always, always, always put in your units with your numbers when you're substituting in values. Minus 20 feet over, or the corresponding times, 3 seconds minus 1 second. So 60 minus 20 is 40. Over 3 minus 1 is 2 seconds, so 40 feet over 2 seconds. This works out to be 20 feet per second. Now, I could go and draw the displacement for that interval. You can just draw it like this here. This would have been my delta x here, and it would be equal to plus 40 meters. So I started at 20, I ended up at 60. I displaced 40 meters to the right. So I could draw a matching average velocity vector. Let's use orange. Say that. And that would correspond to my 20 feet per second. Now wait a minute, you say. Or sorry, not 40 meters up there, obviously, 40 feet. My bad. Now wait a minute, you might say. You drew the 20 longer than the 40. That doesn't make sense. But keep in mind, we can't compare these. This is in feet. This is in feet per second. We cannot meaningfully compare two numbers that have different physical dimensions. So you just have to pick different scales and draw them. So the only thing you can ever say is that the average velocity vector will always point in the same direction as the displacement vector, because our delta t's will always be positive. So this will always end up being the same sign as whatever delta x is, because delta t will always be positive. So if delta x points to the right, v bar points to the right. If delta x points to the left, v bar points to the left. And that's all we could say. I could just as easily chosen a scale where my v bar was shorter or the same length. It's just a different choice of scale. Now, among things with compatible units, you do have to, it's good practice to share common scale here. Now, something to be careful about is the difference between that and the average speed something would be going. So let's just go and take a look at that. The average speed something would be going would be the absolute value of v bar. Because remember, speed is a scalar. It simply says how fast you're going without caring about direction. So if I take the average, if I take the absolute value, that throws away any minus signs I might have, so that I'll always get a positive number. But remember, when you do that, you have thrown away direction information. So for instance, we could have one runner going to the right at, say, I don't know, 5 meters per second. And I could have another runner going to the left at also 5 meters per second. And we'll say these are average speed, average velocities. So here I'd be putting in minus 5 meters per second because we're going to the left. But here, the average speed of this runner is 5 meters per second. and the average speed of this runner is also 5 meters per second, no minus sign. So just because the speeds match does not mean the velocities match. Speeds mean you're going at the same speed, that both objects are going just as fast, but since we've thrown away direction information, we do not know if the velocities are the same unless we have other information to figure that out. Okay. So we've seen a lot of ways to represent motion. For instance, we've seen that we can draw a, oops, sorry about that. We can draw ourselves a motion diagram of something. Say something like this. T equals 0, t equals 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. We'll just go say this is x equals 0, x equals 10 meters. So this would be about x equals 30 meters, x equals 50 meters. This looks to be like maybe about x equals 65 meters, and then finally about x equals 75 meters. So one way I could represent the motion is just by drawing the dots, like so. Another absolutely equivalent way to represent the motion would be if I were to make a table of it. So I could make a table, time in seconds, against position in meters. And here I don't need to write down the units because I've already written the units down here. So I can just write the numbers down. Putting the units in parentheses here is already telling us what the units are, so we don't need to write them down again. So 0, 1, 2, 3, 4, 5, like so. And then I can just fill out the grid. 0, 10, 30, 50, 65, 75, like so. So I could either draw the dots, or I could draw a table. And if I have the dots, I can get the table. If I have the table, I can get the dots. And another representation that physicists really, really like using a lot is to make a graph. Now here, instead, in math classes, a lot of times you'll be told this is always x, this is always y. Physicists are a little more loosey-goosey about it. Here, we would typically put time in the x-axis because that's the thing that is going to be changing. And then what's going to be changing in response? That would be the position. So time in seconds, position in meters. All good graphs should have a title, right? So we'll just say x versus t. So here, the thing on the vertical axis always goes in front of the verses. The thing on the horizontal axis always goes after the verses. So I can go ahead and draw this out. 2, 3, 4, 5. So 0, 1, 2, 3, 4, 5, like that. That 4 is kind of sketchy. There we go. Let's see, I need to go up to about 75, so let's go up by 25s. Sure. There we go. So 25, 50, 75. Then I can look at this table and play battleships to fill this out. So whoops, sorry about that. At time 0, position 0. So I put a dot at 0, 0. That represents that value right there, which says at time 0, the object was located at this point in space. Time 1, position 10. Okay, about like so. So now this dot here, when you read this, what you have to do is you have to look down and see, okay, down, I hit 1 what, 1 second. Across would be about 10 what, 10 meters. So this is telling me at t equals 1 second, the object was located at x equals 10 meters. So in our motion diagram, sorry about that, in our motion diagram, it would be over here. So even though you see the dot up and to the right, the physicist would look at this and just say the motion is purely to the right, because this right here is indicating an increase in time. All this up here is indicating an increase in the x-coordinate of the object. Okay, t equals 2 seconds, it's located at x equals 30, so I'd put a dot there. T equals 3 seconds would be at x equals 50, so I'll put a dot there. T equals 4 seconds, it's located at x equals 65, so I'd put a dot there. T equals 5 seconds, it's at 75. So there we go. Maybe we can draw that dot just a little better. Yeah, about like that. So there we go. So again, when you look at this, what you're going to say is, oh, okay, here, this went up a lot over some time interval. That means the position increased a lot. And sure enough, if I look from 2 to 3, the thing moved to the right a lot. Whereas, say, when I go from 4 to 5 seconds, the dot went up a little bit compared to the previous dot. So that means the position to the right increased a little bit compared to the previous position. So when you see this, when someone draws a graph like this is the sort of thing that you should be trying to construct in your mind until you get comfortable reading the vocabulary of this to see, oh, it's going slower here, faster here, slower there. But to look at this and say that all the motion is to the right in this example. Okay. So this gives us a bit of a clue here. If I go back just for a hot second and look at the definition of average velocity, delta x over delta t, if I think back to that graph, this delta x would be the rise, that delta t would be the run. So at the moment, we only know how to do this if we have straight line segments. But if I have a graph of position versus, oops, sorry about that. If I have a graph of position versus time, say like something like that, as long as I've got segments that are straight lines, I know how to find the average velocity in any of those segments. So we'll just say x versus t, and I'll just mark off these points here. So let's say 0, so this is t in seconds, this is x in meters. So we'll say this is 1 second here, and this is 10 meters. This is 3 seconds here, and that's going to correspond to 15 meters. Not even, yeah, we'll say 15 meters. Be a little generous to myself. And then this is like maybe 3.5 seconds. And we'll say that that corresponds to about 30 meters roughly. Okay. So for each of these time intervals here, I can go ahead and calculate the slope. So right here, over this interval, if I look here, we know that the slope would be equal to the change in x. Sorry about that. The change in x over the change in time for this interval right here from 0 to 1 second. So that would be x final minus x initial over t final minus t initial. Well, my x final is 10 meters. My x initial is 0. My t final is 1 second. My t initial is 0 seconds. So I get 10 meters per second. And so that would be the average velocity that the thing moved over the first second. Now let's go ahead and look at the rest of these intervals. Now technically you can just pick any 2 points on here. I'm just picking the endpoints because I know them. So that's for time interval 1. We'll even say V1 bar like that, just keep it straight. We'll call that time interval 2. This is time interval 3. So for time interval 2, V2 bar would be, again, delta x over delta t, which is, again, x minus x initial over t minus t initial. But now we got to be careful. So putting in the final values shouldn't be too bad. That's going to be 15 meters. But what's the initial value? The initial value is the value at the beginning of the interval, which is 10 meters. So this would be 15 meters minus 10 meters. What's my final time? 3 seconds. What's my initial time? Again, at the beginning of the interval, 1 second. So this will be 5 meters over 2 seconds is 2.5 meters per second. Then finally, for interval 3, we can go ahead and calculate V3 bar. Same process, delta x over delta t for that interval, so it'll be x minus x naught over t minus t naught. Put in the values. The final position was 30 meters. The initial position was 15 meters. The final time was 3.5 seconds. The initial time was 3 seconds. So this is 15 meters over half a second. This will work out to be 30 meters per second. Okay. So with that, I can go ahead and construct the corresponding velocity versus time graph for the same motion. So V1 is 10 meters per second here. So let's go ahead and just start drawing. So here now, instead of plotting position against time, I am plotting my velocity versus time. So this would be in meters per second. Again, the time will be in seconds. V versus t. And yes, I'm intentionally dropping the bar. It turns out that the velocity at any point in the interval is the same as the average, because anywhere along here the slope is always the same. Okay, so in the first interval, that's from 0 to 1 seconds. That was at 10 meters per second. Okay, let me just put in some values here again. So from t equals 0 to t equals 1, we're going at 1 meter per second. Then, let's say 2, 3 seconds, and we'll say 4 seconds. Then from t equals 1 second to t equals 3 seconds, there we go. The graph would look something like that, just an unchanging value at 2.5 meters per second. Then finally, for the last half second of motion, it should be going constantly at 30 meters per second. So this would be the corresponding velocity time graph, and you don't need to connect these. And also, I'm not going to get into a big stink about drawing open or closed circles or anything like that. But this would be the corresponding velocity time graph. So this graph will always give you this position time graph will always be associated with this velocity time graph, but it doesn't necessarily work the other way around. And that's because I could have all these same slopes, say if this were shifted up by 10 meters. I would have a whole nother curve that follows the exact same shape, has all the same slopes. So if I have a position time graph, I can always get the velocity time graph. From the velocity time graph, I can do this backwards and say the value of the velocity time graph at any time is the slope of the position time graph at that same time. But I will need one extra piece of information. I'll need the initial position, and I'll need that just so I can set the graph. Because for instance, with this graph here, it could have been this, or as I was mentioning earlier, if we'd started x equals, sorry about that. We started at x equals 10. This graph here would have exactly the same slopes that the pink graph has. So it'd have the exact same velocity time graph. So that's why we need to know the initial position, just so we can anchor it. Okay, the pedants among you will say it doesn't have to be the initial position, and you're correct. It will do to just plain know the position at any particular time. In physics, however, that's typically going to be the initial position because you tend to know that. All right, there is another way, though, that we could go about finding the position. Again, we still need to know the initial position, but we could go and find later positions with a little trick here. If I look at the definition of average velocity, remember that was the change in position over the change in time, right? I can rewrite this and say that delta x is equal to v bar delta t. Okay, how could I interpret that graphically? Graphically, say for this interval right here, it would correspond to the area of this box, right? It's v bar high here by delta t wide. So the area of the box here, delta x, is the average velocity at that interval. And this only works if you're going at constant velocity. In a later class, we'll refine it, or at least over segments. In a later class, we'll refine it. Times the time for that same interval. So in this example here, we could say the displacement was 10 meters per second times 1 second is plus 10 meters. And let's check. Is the final value 10 meters greater than the initial? Start at 0, ended up at 10? Yep, it is. So that's one way I could do it. Once I have the initial value, I could just draw these boxes, calculate the areas of the boxes, and use that to figure out how much higher or lower the next point should be in the next interval. There is one caveat, and that is if I had some motion, say, that looked like this. So let me go back to my black pen here. So if this is my velocity, again, let's just say meters per second, but we don't have to be too fussy about units. This is seconds. Let's say I was looking at an interval here. So this time elapsed here would be my, whoops, sorry about that. This time elapsed here would be my delta t, and this would be my delta v. Let's just make it concrete. Let's say this is 2 seconds here, and this is -8 meters per second. I could do the same trick for finding the area, and it would be valid. However, I've got to be a little careful about that. Because this delta v is negative, and so areas that are measured below the horizontal axis we have to define as negative. Oops. So this is just a definition to make this little trick work, but we can do it. The displacement would be equal to this area under the curve, we usually call it. So this would be the, let's see, it's got a length, it's got a height of -8 meters per second, a length, well, then the length is 2 seconds for our rectangle, and so -8 meters per second times 2 seconds is -16 meters. So we'd look at this and conclude that the object had moved 16 meters to the left. And that makes sense because the velocity was -8 meters per second, so it told us that we were going to the left. So we knew we were going to the left. So in order for this area trick to work out, we have to say that areas that go under the line count as negative. Okay. So with all of that, we're going to finish up with a quick definition of uniform motion. Oops, sorry about all that. There we go. There are a bunch of equivalent definitions. So we can say that motion is uniform, straight line if we have successive displacements. Are the same for equal time intervals. We can also say that it's uniform if its position time graph is a straight line. Or we can say its velocity is a constant. Now, although we haven't rigorously defined instantaneous velocity, which is what we mean when we talk about velocity without an adjective in front of it, I think it at least makes some kind of sense here. If I go ahead and plot my position versus time here, for instance, let's do that. All right, so we can look at this and say, yeah, sure, over equal times, this drops the same every single time. So it checks that box. These are all turn out to be equivalent statements. Sorry about that too. It's a straight line. Yep, sure enough. Velocity is a constant. Well, the average velocity is the same, right? But I can pick any interval and calculate it, and it would be the same because the slope is the same everywhere. If it's the same absolutely everywhere, then we can say the velocity was never changing. So we get that the velocity is equal to the slope of the position time graph, and that the velocity is the same at all times. So that is our definition of uniform motion for now. Later, we will go ahead and extend that to say that it's equivalent to saying the object has no acceleration. But that is for a later video, and so I will catch you all on the flip side.